Hi everybody, it's return from spring break. Welcome back. I hope you all stayed safe and relatively isolated during the break, but in any case I hope you had a relaxing time. Today we're going to do a thing called the method of partial fractions. Um, this will probably be the last thing that I technically call an integration technique we'll do, although there's one more section in this chapter we'll look at. Two more sections. One is about numerical integration, and the other about what are known as improper integrals where maybe the limits are infinite, which is a little strange, but we can handle it using limits. So what's this thing for today, the method of partial fractions? Partial fractions actually draws together a bunch of threads from things that you did in, well, even going back to high school. It's a technique which is used to integrate any rational function. So integrate integrals of rational functions. So first, I guess, let's remind ourselves of what I mean by a rational function. Quickly running out of board space. What is a rational function? Well, it's a rational function is, it sounds like it should be, it's a ratio, but it's a ratio of a particular kind, where both the numerator and denominator are polynomials. So you might say something like r of x, let's try that again, r of x is equal to, say, p of x over q of x, where p and q are polynomials. I guess I should say p of x and q of x are polynomials. I'm going to have to abbreviate that word, but you know what that is. So r of x equals that, our polynomials, is a rational function. Finally, ending the sentence. All right, so what does it look like to integrate a rational function? The first thing you're going to have to deal with is that the method we're trying to learn right now works only if the numerator is smaller in degree than the denominator. So partial fractions is just for that scenario where the numerator is of lower degree than the denominator. This is a statement of what I just said. The degree of p of x will be less than the degree of q of x, and that's strictly less than. So that's a pretty strong restriction, but it's one that we can actually reduce to rather quickly. Any rational function can be put into the form of a polynomial plus something that satisfies that. And so the polynomial part will be able to handle no problem, and the rational part that satisfies this, that'll be golden. Okay, so let's see if I can write this. It can be written as, let's see, we'll need one polynomial, well, let's call it, start again, r of x, that'll be the rational function, will be equal to a polynomial plus a p of x over q of x, where all three of these guys, fp and q, are polynomials, and degree of p is less than the degree of q. And how do we do that? Can I just leave the arguments off of these things? Call it fp and q are polynomials. Well, really what I said above, the degree of p is the numerator, right? So the degree of p is going to be less than the degree of q. Yeah, so the way you do that is actually just do long division. And my suspicion is that it's been a little while since everybody's done long division with polynomials. So I'm going to do first a little refresher on what that looks like, and then we'll proceed to figure out how partial fractions works. All right, so I made up a rational function. I hope this will work out well. I'm doing this without a net. I haven't tried it out in advance, so let's see how it goes. But anyway, I've got a cubic polynomial over a quadratic polynomial. And what we're going to do then is do division to write this in the form that I just showed. What gets divided into what? It's the way I'm used to thinking about this is sort of harking back to the third grade or maybe fourth grade. Maybe it was fifth grade. Anyway, where you do division with numbers, like how about 7 into 52? 7 goes into 52, well, it doesn't go into 5, but it goes into 50 7 times. 7 times 7 is 49, and then you subtract and you get a remainder of 3. So we write 7R3 when we're doing this kind of thing. Right? But we're going to do that with polynomials. So I've got it in the form x cubed plus 1 over x squared minus x plus 2. Which fills which role? Which is the thing outside the little L-shaped gizmo, and which was the one inside? And I guess I just want to think about what fraction would we be dealing with if it was, you know, if we were to set up that division problem. It would be 7 in the bottom and 52 in the top, right? To get that, we would divide 7 into 52. Well, this answer would be 7 and a little bit. 7 with some remainder, okay? So we're going to want the thing inside the L to be the numerator and the thing outside the L to be the denominator. I consider that scrap work. I was just trying to help you remember how the process of long division works. So I'm going to feel guiltless in erasing that, and then we'll set up the long division problem. Oh crap, what did I just say? Yeah, x cubed plus 1 is inside the thing, and x squared minus x plus 2 is outside the thing. Now, I'm going to give you a tip that I think will come in handy if you find yourself doing many of these problems, which is, it's kind of an accountancy thing. You want to leave space for all the possible terms that could show up. This is a cubic divided by a quadratic. There could be particle stuff that's x squared and then x to the first power and then constants. So writing it like this is probably a poor choice. I should sort of think about this as there's some room for the quadratic, there's some room for the linear, and here's the plus 1 on the end. Okay? Great, so how does long division with polynomials work? Actually, it's funny, it's actually easier than it is with numbers, because all you have to do is look at the leading terms. This guy has a leading term of x cubed, this guy has a leading term of x squared into x cubed, well, that goes x times. So we get an x. Notice how I'm putting it in the column where things would have degree 1. Then, like we did with numbers, you multiply back. So x times x squared gives us x cubed. X times minus x, that's minus x squared. X times plus 2 is plus 2x. And that is going to be subtracted from what's above it. Yeah. So yeah, we'll subtract that. And it's nice, by design, x cubed and minus x cubed are going to kill each other. Here we've got nothing minus x squared. Double negatives there, right? So that's positive x squared. Then minus 2x. And then plus 1. Because that has nothing under it to subtract from it. All right. Oh, it's close, but no cigar. X squared goes into x squared. That is just looking at leading terms. It goes once. X squared over x squared is 1. Multiplying back, we get x squared minus x plus 1. Oh, excuse me, plus 2. And when we subtract that from what's above it, you'll get the x squareds are gone. Minus 2x minus x. Yikes. That's minus 2 plus 1x, or negative x. and then 1 minus 2 minus 1. And now I hope you know, but I definitely know to stop now, because what we've got here is a polynomial whose degree is smaller than the divisor. And that's when you stop with regular numbers. When we're doing division with numbers, you stop when the remainder is literally less than the thing. With polynomials, we use their degrees to tell which thing is smaller. So the degree of that is 1, the degree of this is 2. We can quit. So this is our quotient, and this is our remainder. And that means my R of x up there can be written as what we got for the quotient, x plus 1, plus a root of the remainder divided by this. Now actually, my remainder ended up being negative of something, so let's write it as minus x plus 1 over x squared minus x plus 2. But the point of the process is that we've re-expressed R of x so that you get a polynomial and then a fraction that does obey the rules that I asked, or the condition I asked about, that the degree of the top is smaller than the degree of the bottom. And if you are integrating this stuff, we can integrate this, and we can integrate this, and we're going to be able to integrate that. Okay, so that's what the method of partial fractions is about, is letting us integrate something of that form. Cool. Well, I just talked about reducing the problem we had to polynomial stuff plus a rational function that looks like that, the degree of the top smaller than the degree in the bottom. But here's what I get for working without a net. I chose poorly about that polynomial that's in the bottom. X squared minus x plus 2 is, well, it's actually something that we can do, but I don't want to do this as our first example. Why? Because this thing is what's known as an irreducible quadratic. And while that's fine, and eventually we're going to want to be able to deal with irreducible quadratics, right now it makes me sad. So what is an irreducible quadratic? This is something, again, you probably learned in pre-calc, if not back in high school. Here's a plot of that function. I hope that's framed properly in the camera. I can't really tell, but look, it's if you plot it yourself, you'll see it doesn't have any zeros. It never hits the x-axis. That's what makes it an irreducible. Now, irreducibility is actually a question that's dependent on context. We're thinking about real polynomials and whether they have real solutions, and this one doesn't. It does have zeros, but they're complex numbers, so we're going to avoid that for now. So yeah, we're gonna stop looking at that one and do the easy case that I do know how to do, which is when the thing does in fact does have real solutions. That is, it's not irreducible. Another way to say that most often is that it can be factored. Before I leave this guy though, how could you tell, without maybe pulling out the graphing calculator, that this was an irreducible quadratic? Do you remember the quadratic formula, which has, let's see, negative b plus or minus square root b squared minus 4ac. That's divided by 2a. If you have a negative number under that radical, that's when you get complex numbers as the solutions for it. And that's exactly when you're irreducible. So an irreducible quadratic is the same thing as saying that b squared minus 4ac is negative. That's what gives you an irreducible quadratic. So let's check that out on my guy here. B squared, b is the coefficient of x, it's negative 1. We're squaring that, so it's plus 1. And then subtracting 4 times a, there's no number in front of x, so that means a is a 1, and c is 2. 1 minus 8 Yeah, this is -7. That's called the discriminant of the polynomial because it discriminates between the cases where you're reducible versus irreducible. Yeah, so this was a bad one, but let's do a better one. Okay, I'm back with a different problem that actually works for us. This is an example that I was careful to check and it follows the pattern it's supposed to. So we'll see basically the easiest case of the partial fraction decomposition here. You may notice the only difference is I have a minus sign here instead of a plus sign, but it makes a big difference because the resulting polynomial there, x squared minus x minus 2, is no longer irreducible. Let's just verify. What did Ronald Reagan say? Trust but verify. The negative of b is still, I'm sorry, b squared is still minus 1 squared. Minus 4 times a times c, that's 4 times 1 times a -2. And so this is a positive 8 because there's two minus signs there, and 1 plus 8 is 9. So the discriminant of this guy is 9. In fact, that tells you that the distance between the vertex and the roots is 3, the square root of that. Excuse me. All right, so that was just for a check. We don't really need that computation, but I wanted to be sure. I also changed the thing that was in the numerator just honestly to make it work out so some numbers were nicer. Okay, but this is the same spirit, right? It's got a linear polynomial in the numerator and a quadratic polynomial in the denominator. Well, let's proceed to do a partial fraction decomposition. Let me just tell you that the basic tool you're going to use is factorization, something you've done tons of. Can we all factor x squared minus x minus 2? We've got, okay, still x minus 5 in the numerator, but in the bottom that factors as, let's see, I can tell you for sure that it's plus something and minus something, x plus one number and x minus another, because the last times last, that gets you the constant term in the product, is -2. And then you look at the middle guy there and realize that's the result from the outer times outer and inner times inner. Basically the sum of the two numbers I'm going to end up putting here. So it's because it's -2, I know I'm looking for a 2 and a 1, and I want them to add up to -1. That means I want the 2 to go in that slot and the 1 to go in that slot. Did I do it right? Double check me. Certainly x times x will get us the x squared, then we have a plus x and a minus 2x. Sure, that's minus x, and last times last is the -2. Cool. So here's the big tool. The partial fraction decomposition says that you can always re-express a thing like this in the following way. You can write it as some number over one factor, x plus 1, plus some other number. Make my plus signs better. Well, I just made my plus sign worse by doing that. Plus some other number, b, divided by the other factor, x minus 2. That's a sort of theoretical tool. I don't know if we care that much why this is true, but you'll see it in action. It's always possible to find the a and the b. So let's go about doing that. The job to find the a and the b essentially comes down to adding fractions. And of course, when you add fractions, you have to have a common denominator. And what would the common denominator for this pair of fractions be? Well, it would be exactly this denominator we're seeing on the other side there. So what I would have to multiply the top and bottom of this fraction by to get this product of x plus 1 and x minus 2, I need to have a x minus 2 up there and an x minus 2 down there. And similarly on this one, although it's kind of flipped around, I'll need an x plus 1 in the top and in the bottom. So those multiplying by a thing over itself really doesn't change anything, that's 1. But we will then have a common denominator so that we can add the two fractions together. Let's switch back to black ink and we'll do that. That's equal to, well, a times x minus 2 plus b times x plus 1 all over the same denominator that I got on that side, x plus 1 times x minus 2. Groovy. Now, these things are supposed to be equal, so what I've got to do is figure out what numbers work for a and b to actually make them equal. And the thing you'll notice is the first fraction has an x minus 5 in the numerator and that product in the denominator. This other one has a more complicated expression in the numerator, but the same denominator. Well, if two fractions are equal and they have the same denominator, what has to be the case is that the two numerators have to be equal. Let me just write that for a second. Therefore, x minus 5 must be equal to a times x minus 2 plus b times x plus 1. Still looks pretty complicated, but it turns out this is not bad at all. You can re-express this thing so that it looks like a coefficient times x plus another coefficient that would be a constant. And we'll see that the coefficient of x is going to be 1 and the constant's going to be minus 5. Let me do what I just described. What things are multiplying x's? We'll have a b times x here and an a times x there. So all told, that's a plus b times x. And what things are, just multiplying numbers? We'll have minus 2 times a, and we'll have plus 1 times b. So what I know is that this piece right here, the a plus b, has got to be equal to 1, and this piece right here is equal to minus 5. So I just rewrote the system that I had kind of at the bottom of the board up here at the top. A and b have to add up to 1, and this combination, minus 2 times a plus b, has to equal to minus 5. Great. There's several approaches to doing a thing like this, but let me show you the two principal ones that people do. One is called elimination. And the other is called substitution. And I guess I'll do substitution first. Well, that's one word. Okay, so what substitution amounts to is picking one of the equations that seems particularly easy to do this for and solving it for one of the variables. So I would, for instance, solve this for b. B is going to be equal to 1 minus a. Right? That substitution, well, the part where we actually substitute is we replace the b in the other equation with what I just wrote down. So then that means we can say minus 2 times a plus 1 minus a must be equal to negative 5. We can simplify, but we're in a good spot right now because everything in here is either a multiple of a or a number. That is, we've got a linear equation in one variable, a. So that's definitely solvable. What is it actually when we combine like terms? We've got minus 3 a's plus 1 equals minus 5. Can I just take the plus 1 over to the other side and make it minus 6 now? Do you see the solution for a there? A is going to be 2. Now that I know what a is, you can also substitute, replace that a right there with a 2. So what's b? B is 1 minus 2. Okay, b is minus 1. So there's our answers. A is 2, b is minus 1. I'll come back to the original problem, but I do want to show you this other technique for how to do a system like this. It's called elimination. This is kind of nice, and if you're ever going to take linear algebra, this is sort of the first steps in the direction of doing linear algebra, which I have to tell you, I make my living doing linear algebra. That's really a powerful mathematical tool. It doesn't sound like much, just algebra with lines, it seems like, but it's not. It's all kinds of linear phenomena that happen in high dimensional spaces. It's very exciting and yeah, very useful. Anyway, yeah, how does the process of elimination work? You're basically trying to arrange so that you've got something rather like what we have here, that you've got a negative number and a positive number, but you want them to eliminate when you add up equations. So what I'd really like to do is replace that top line, a plus b, with its double. 2a plus 2b would be equal to 2. And then the other line I'll leave the same, minus 2a plus b is equal to minus 5. You can always make this sort of thing happen. Find an appropriate number to multiply one equation by to make it so that when we add the equations, things will just go away. Let's just add the equations now. 2a and minus 2a is, by design, gone. 2b and b, that's a 3b. And what do you get when you add 2 and minus 5? That's minus 3. And you can probably spot from that okay, yeah, b is negative 1, just like we got in the other method. And like before, once you know one of the variables, the other one is just going to fall right out. You can pick whatever thing you want. I probably would go back to the original equation. A plus b is supposed to be equal to 1. So if b is minus 1, a's got to be 2. So we did indeed get the same solution as the other way, but yeah, I don't know. It comes down to preference. Some people like to do elimination all the time. Other people prefer substitution. I'll tell you that substitution is lovely when you've just got two variables. When you start to have more variables, then it gets a little rough. I will come back later to show you how a third technique, which is to basically use technology. You can get your graphing calculators to do this sort of thing, but first let's actually go back to our original problem and solve it. Well, if I've done things right, then we should have this result, that original rational function I was looking at is actually expressible as the sum or difference, in this case, of these two things with one factor of the bottom in the bottom there, and the other factor of the bottom in the bottom here, and we found the a and the b. They were 2 and minus 1. Wow, really? I always get to this point and I'm like, are you sure? So it's a great idea to double check. What would you get? Because maybe I'm questioning this. What would you get if you tried to add these two fractions together? I'd get 2 times x minus 2 minus 1 times x plus 1. Both of those would be designed to be over the denominator we've got there, x squared minus x minus 2. Yeah? So what is this? It's 2x minus x, so that's an x. The bottom, I'll just copy it, x squared minus x minus 2. What is the constant terms? Minus 4, minus 1, that's minus 5. Okay, so yay, it's right, and that's not in question anymore, it's verified. Right? So, what does this let us do? This means that if I were faced with an integral of that rational function, I could instead look at its partial fraction decomposition, and wow, that's going to turn out to be really easy. The integral of 2 over x plus 1 minus the integral of 1 over x minus 2. Well, both of these are dx. Why are these so easy? Well, that the 2 can come up front, and a quick u substitution with u being x plus 1 means this one would be the reciprocal of u, so its antiderivative is natural log of u. So we'll get 2 times the natural log of x plus 1 minus, here we just have the natural log of the x minus 2. course, there could be a constant in there if we don't have limits or whatever. But if you're just looking to find an antiderivative, we had it. So that's pretty powerful, and it can be generalized to more interesting examples. So I think that's what we'll do next. I had said I was going to come in and do a little extra stuff on some of the other more general ways of dealing with partial fractions, but it occurred to me that I promised, and I want to come through on that promise to show you other ways to be able to solve for A and B, the coefficients in the partial fraction decomposition. So let me start by just copying the thing we had to deal with. It was x minus 5 was a times x minus 2 plus b times x plus 1. And there is a technique that is actually really straightforward and quick and works on this sort of thing. Sometimes can be used in some of the other techniques, some of the other methods, but certainly works when we've got this simplest case where the quadratic and the bottom factors. And it is this. You just pick judiciously values for x and evaluate there. Now, what do I mean by judiciously? Well, if you picked x equals 2, this term would be 0, and so there would be no a in it. So think what happens when you look at x equals 2. X minus 5, that'd be 2 minus 5 is negative 3, equals, that whole part is gone because it's a times 0. And the other part would be b times 2 plus 1. I think we've even seen that before. B times 3 equals minus 3, so b is equal to minus 1. What value of x would we choose to make this part go away? Instead of at x equals 2, we could look at x equals minus 1. And then, let's see, minus 1 minus 5, that would be minus 6 equals a times, okay, minus 1 minus 2, right? That's minus 3. And b times 0. I don't even know why I wrote that, right? For the reason that we were evaluating at x equals minus 1 was to make that 0, so that part would go away. And this gives us a solution, a value for the a variable. It's a equals 2. So that's pretty cool. There is a very nice general way to solve this sort of thing using the graphing calculator, and I also want to show you that, but that needs a little bit of a preamble. We had developed the linear system that a plus b was equal to 1 and negative 2a plus b was equal to minus 5, right? And it's well, there's a shorthand for that sort of linear system. It's called a matrix, and basically what a matrix is a table of numbers. Matrix actually is Latin for table. So you make, usually in square braces, you make a table that contains kind of the important bits of the system of equations. Now, do you notice how I write a first and then b second in both equations? If you're systematic like that, then you'll always have just a coefficient times a in the sort of left side, plus there'll be a coefficient times b, and then finally there'll be junk on the right-hand side. You could sort of completely recover that system by just writing down what all the coefficients are. In that top row, it's 1, 1, and 1. And the bottom row, it's minus 2, 1, and minus 5. So that table of numbers completely encapsulates the information in the linear system. Okay? So in a graphing calculator, there's a way to input a matrix and then to manipulate that matrix, and it basically will tell you the solution to the linear system. So do you see the word matrx above the x inverse key? That's what you're going to need. Interesting. For some reason, I have set this one up to already be a 2x3, but it's probably got different values in there, yeah. So you can edit that size, but this is a matrix that has 2 rows and 3 columns. Okay? So 2 by 3 is correct. What we want for the entries, though, well, the top entries were 1. Each time you hit enter, it just moves you along. They were all 3 ones, right? It was 1 times A plus 1 times B equals 1. And in the bottom row, it was negative 2 times A plus 1 times B is equal to negative 5. Cool. So I've just edited that matrix. Let me just quit out of this screen. When you're on the plane screen, you can also use the matrix menu to do other things. First of all, I'm seeing the matrix A right now. And you just pull up its name and then hit enter and it'll display it. I'm going to double check the numbers. 1, 1, 1, and minus 2, 1, minus 5. Yeah, that's the right stuff. Now, if we could only do that, it wouldn't be really much help, but there's a function in the matrix menu where you can do math on a matrix. There's a bunch of them, but the one that we're really interested in is called RREF. It's down here. RREF. So what RREF does, well, actually, let me just show you what RREF does. I need to pull up the function and then go back to the matrix menu to get the name of the matrix we're using. It's A in square braces. What does it do? It converts that matrix into one that has the exact same solution set, but is a little bit different. Notice how you've got a 1, and then a 0, and then a 2, and then a 0, a 1, and a minus 1. Those zeros in the off diagonals and the 1s on the diagonal mean that the matrix is equivalent to, actually let me just go ahead and write it down. This matrix I was just illustrating things with is the same linear system as the one we just got. What were those other numbers? 2 and a minus 1 were here and here. Okay? And if you reinterpret what that means as a system of equations in the variables A and B, we have 1 times A, well, it's A, 0 times B equals 2. Again, that's kind of silly. A equals 2. Right? And the second line of that matrix is 0 times A plus B equals minus 1. That part's silly. This one says B equals minus 1. In other words, in that RREF version of things, you can just read off the answers for A and B out of the matrix. So if you like the calculator, you can use it and its matrix arithmetic to get you the solution to a system of equations, or you can do this bit I talked about before of picking particular x values where if you evaluated them, the result is easy to see. Okay, so pushing on to the more exciting kind of forms for partial fraction decompositions. Let's look at it. This is the last thing in this chapter. It's a little box in the back of the chapter that kind of summarizes what's going on with partial fractions. What we've looked at so far is this first one. When you have simple linear factors, you create something in the partial fraction decomposition that looks like an unknown variable over that factor. So that the x minus r is supposed to make you think x minus a root. Okay. There's some other stuff that can happen. For instance, look at number 3. That's the scenario that I was accidentally got into with my first example. You'd have an irreducible quadratic factor. Well, each irreducible quadratic factor, you have to, rather than just having a single number over it, you have a linear thing over it. So ax plus b. That means for each irreducible quadratic, you're going to get two variables. The other thing that can go south on us is we may have repeated factors. So you could have the same linear factor multiple times. You could have the same quadratic factor multiple times. And they handle these in two different cases, number 2 and number 4. A repeated linear factor, well, they're presuming it went m times. That'd be pretty huge. So think about it as just being two copies of a linear factor. Then you just have that much, right? A constant over x minus r, and then another constant over x minus r squared. You'd still get, something that was quadratic if it had multiplicity 2, and you'd still get two numbers out of it. So that sort of makes sense in that regard. And a very similar thing is happening down here. When you have a repeated quadratic factor, you'll get extra variables, two of them at a time, but extra variables for each power of that repeated quadratic factor. So I think it would be best for us to return to the whiteboard, and I'll show you some examples of both of these. Right, so the next example I'm going to do will show you what happens when you have repeated linear factors. So suppose we had the integral of x over x squared plus 2x plus 1 dx. Perfectly reasonable rational function. It certainly has area under it, so we ought to be able to get an integral. I hope you notice that bottom is something that factors as x plus 1 squared. Okay. So what we've really got is x over x plus 1 squared dx. So the partial fractions decomposition, when you have a repeated factor like that, is that you can replace the integrand with something over x plus 1 and something else over x plus 1 squared. Now in the textbook they call these A1 and A2, but I think it's just a little easier to call them A and B if we know how many of them there are. They were trying to deal with the case where you might have m different copies because the power of the number of repeated copies of x minus the root was large. All right, but we'll have something like this. Except we need to figure out what a and b are. So notice that we're looking for this equation to be true. A times x plus 1, a over x plus 1 plus b over x plus 1 squared is equal to x over x plus 1 squared. That is, this is what we want to have to be true. We've got to use that to find what a and b are. This side can be combined nicely. Just you need to have an extra copy of x plus 1 on this side, and then both in the top and the bottom, and then we'll have the same denominator, right? So then that gives us a times x plus 1 plus b must have to be equal to x, because both of these fractions have the same denominator, x plus 1 squared, so the numerators have to be equal. All right, what does that say? That says that a times x plus a plus b, because you have an a there and a b there, is equal to x. So what do you deduce from that? Well, this one's particularly nice because it says a times x, and this has a 1 times x, so a must be equal to 1. Now what does a plus b have to be equal to? Well, there's nothing on this side, so we have a equals 1. Just by inspection, we get the solution a equals 1, and b has to be something so that a plus b is 0. So there's minus 1. Okay. So let's suppose that we had done this work on a separate sheet of paper or something, because I want to continue going without doing a new screen. What we've got then is the integral of 1 over x plus 1 plus negative 1 over x plus 1 squared dx. Now, of course, we can separate that into two integrals. Integral of 1 over x plus 1, and let's pull that minus sign out front and make it minus the integral of 1 over x plus 1 to the second power. Both of these are dx. And both of them are completely doable, right? The first one is the natural log of x plus 1. I should say absolute x plus 1. The second one, it's really a quick u substitution. I don't think we need to do it out. We've got u squared in the bottom of a fraction, so that's u to the minus 2 power. And since this is this u is just a, well, x plus 1, it's got the same differential that x does. Du is equal to dx. All right, so what are we subtracting then? That's the negative second power. When you add 1 to the power, you get negative 1. So we'll have 1 over negative 1 times u to the negative 1. That's kind of a silly way to write it. We've got two minus signs, so we're adding 1 over x plus 1. Let me just copy it in over here so that we don't have to do a whole new screen. So that's an antiderivative. If we had limits, we'd just use that. If you were just doing a indefinite integral, you'd need to put a plus c on this. Okay. So the last example I'm going to do today is actually going back to the first one I did. Remember, I had ended up with this thing that didn't work out very well for me because I had chosen a poor, an irreducible quadratic, but that's what I want to illustrate now, so we can handle irreducible quadratics. It was x squared minus x plus 2, and we had in the denominator x plus 1 in the numerator. Yeah, I'm just checking that it was the same thing. Okay, so this is an irreducible quadratic downstairs. We already know that. That means we can use the partial fraction decomposition for an irreducible quadratic. It means it has something of the form ax plus b in the numerator for that corresponding to that factor, and the irreducible quadratic, excuse me, I just wrote that wrong, x squared minus x plus 2 in the denominator. So what are a and b? Well, in this case, there's no work to do because ax plus b has to equal x plus 1. So a has to be 1 and b has to be 1. They're both 1. So we got lucky on that one. Usually these things will come up as this irreducible quadratic is part of a larger polynomial, and you may have something uglier up there. You may have to do a little work, but it'll be stuff that can be handled by the same methods we did before. The worst case scenario is throw them all into a matrix and use the calculator to get an answer. You may have multiple variables if you're in a really complicated one, but typically we'll only deal with things up to maybe the 4th degree. But for this one, just to run through this example, a is 1, b is 1. Cool. Well now, how do we approach that? It actually is a completely doable integral. What you might think about is a u substitution. If u was that thing in the bottom, then what would du be? It would be 2x minus 1, and that term would go away. So 2x minus 1 dx. we have x plus 1, not 2x minus 1, but if we could make du appear up here, then that would be a good step. So this integral can be, let's see, the first thing I'd like to do is just double everything in the top. So 2x plus 2 in the numerator. Well, that means to keep things balanced, we'll have a half out front, and then the same denominator we've had all along, x squared minus x plus 2. Good, but not quite good enough. I want to see 2x minus 1. What I've got is 2x plus 2. Just, again, kind of make it happen. Take the 1/2 and the integral, put 2x minus 1 here. Okay, but that would be wrong because we had 2x plus 2. We'll just add on a 3 and now it's good. Right? All over x squared minus x plus 2. Think of this as maybe I should write some parens to group things. All right, so what we got now is something that can be split apart, and you get two integrals out of this. Let me split it apart and also distribute the integration. So it'll be 1/2 times the integral of 2x minus 1 over our irreducible quadratic. And we'll also have that 1/2 applies to both of these, so a 3 over x squared minus x plus 2. This one's dx. I keep forgetting my d whatever, so that one needs a dx in there too. Okay. All right, so the first of these integrals is du over u. So that's easy. That's natural log of absolute u. But what about the second one? Well, that can, by completing the square, be turned into a form that we can deal with. 3 times the integral. I'm just going to pull that 3 out. Completing the square on this guy would involve x minus 1/2 squared, which would get us a constant of 1/4, positive 1/4, but we've actually got a 2, so we need to add, was that 7/4? And this is the kind of thing we can do with the trig substitutions we talked about last time. This is x minus 1/2 will be our u, and that'll be, well, it's the square of root 7 over 2. So u will be x minus 1/2, and a will be square root of 7 over 2. Do you see that as a tangent substitution? I hope so. We've got the sum of a variable squared plus a square of a constant. And I'm not going to finish that one. I think that's a great exercise to leave to you. So that's it for today.